In today's lecture, we will show how the Fourier transform technique is used for constructing MRI imaging. We also see the sampling process and the relationship between the K-space and the image space. An MRI image is made up of waves with various amplitudes and frequencies that come from every pixel in the image plane. We must decompose this mixed MRI signal into its constituent waves and identify the frequencies and the phases of each wave in order to construct an MRI image. We are aware of the frequencies and the phases of each pixel's wave, since the phase encoding and the frequency encoding gradients fix them. The signal intensity of the wave with a specific frequency and the phase can therefore be matched to the pixel and the image plane once the mixed MRI signal has been separated into its component waves. The Fourier transform technique can be used to decompose the mixed MRI signal into its constituent waves. The Fourier transform produces the MR signal's spectrum, which shows the kinds of waves with various frequencies and amplitudes that make up the MR image. The signal intensities from each pixel can be determined once the spectrum of the mixed MR signal has been produced. The signal intensity of a particular pixel reflects the spin relaxation times in that pixel. Using the Fourier transform technique, data in time-space can be converted into data in frequency space. The MR signals are time-varying RF waves. These MR signals can be transformed into the frequency-dependent MR signal spectrum. The frequencies that make up MR signals and their relative intensities are shown by the spectrum. We can get the signal intensities for each pixels and construct the image using the Fourier transform. The spectrum G omega is given by the Fourier transform of the function ft as follows. This is the function f, which is composed of the 4 sine functions with the different amplitudes and different frequencies. We can decompose these time-varying waves into a spectrum using Fourier transform technique. So in the spectrum, you can see that frequency 1 Hz has amplitude 1, and frequency 2 waves amplitude 2, and 3 and 4. In this way, we can decompose the time-varying signal into the spectrum of the wave by using Fourier transform. The equation below, this equation, links the time-varying signal ft in the time domain to the frequency domain spectrum G omega. The spectrum G omega contains information about the amplitudes of the waves of various frequencies that contribute to the signal's formation. Inversely, the time-varying function ft is reconstructed if the spectrum G omega is provided. This is performed through the inverse Fourier transform, which is written mathematically as this equation. Let's see the rectangular window function. This function is defined by this equation. G omega is 1 within minus omega 0 and omega 0, otherwise 0. Okay. This looks like window, so this is called rectangular window function. The wave that consists of frequencies with equal amplitudes between minus omega 0 and omega 0 is called the rectangular window function. This window function can be Fourier transformed to be ft. This function, window function G omega, is spectrum, and ft is time varying wave. If we put this G omega here, we can get this function. This is called sinc function. So this is shape of the sinc function. This is not signed the sinc function. The sinc function is the window function's Fourier transform. Okay. The RF pulse and the echo signals have the form of this sinc function. So RF signal and echo signals looks like this. Two extreme frequencies in the window function here are f0 minus delta f and f0 plus delta f. Yes. If the window function's center frequency is set to be f0. Okay. As a result, here omega 0 in the window function corresponds to delta f. The RF wave's bandwidth is 2 delta f. Okay, so its bandwidth is 2 delta f. Now let's see the delta function. The delta function has the following properties. At omega equals 0 has the amplitude, so infinity, otherwise 0. So delta function has amplitude delta omega, amplitude only at omega equals 0. So integral of delta function from minus infinity to infinity equal to 1. This means that the area under a delta function is unity. Next property, f omega is multiplied by delta function. Then we have f omega 0. And delta omega, this delta omega is has some amplitude only at omega 0, so we get f0. So this property means that integrating any function f omega multiplied by a delta function picks out the value of f omega at the location of the delta function. Okay, so location of this delta function is omega 0. So if we multiply a certain function f omega by delta function at omega 0, then integral of this one gives the value of function f at omega 0. Here, this is 0, right? Delta omega is located at omega 0, so the function f at omega 0 is the result of this integral. The Fourier transform of a constant function, this constant function is the delta function. The constant function remains constant across time. Okay? So it is a type of DC signal with a frequency of 0. As a result, the delta function's Fourier transform reflects this behavior. So DC signal has the frequency of 0. So if we transform of delta omega, then we have 1, and it's constant, right? And the Fourier transform of constant, this function becomes delta function. So constant function and the delta function are Fourier transform pairs. If we do Fourier transform of this constant function, we can get delta function, and inversely, if we do the Fourier transform of this delta function, we can get constant function. So these two functions are Fourier transform pairs. K-space and image space, real space or image space. The MRI signal is made up of signals generated at various points through the slice. The signals at various points in the slice must be recognized in order to build an MRI image of the slice. The encoding process is required for this. Gradients of phase and frequency encoding are used to accomplish this. When the frequency gradient is applied, MRI signal is acquired. This signal acquisition procedure is repeated 256 times, producing a 256 times 256 pixel image with a varied phase encoding gradients. So we have to repeat data acquisition 256 times. First, we apply phase encoding gradient, and next we apply frequency encoding gradient for acquiring the MR signal. And the phase encoding gradient should be changed every time, 256 times. After applying the phase encoding gradient GY for tau seconds, the phase change of theta equal gamma gy y tau happens at a point y. So the frequency is given by this one, and the phase is given by multiplying frequency by time. So this phase encoding gradient is applied along the y direction. So the phase change is given by this form. So y direction, along y direction, and the duration time of gradient is tau, and that is the slope of the phase encoding gradient. Then the MR signal is obtained by applying the frequency encoding gradient Gx for the time of t along the x direction. The phase change of gamma gx occurs at the location x as a result of this gradient. As a result, the phase of nuclear spins at the point xy is written as, right? So this is phase change due to the frequency encoding gradient along x direction. This is phase change due to the phase encoding gradient along y direction. Okay. Here, gy is a variable that should be modified every time an MR signal is acquired. So we have to change the slope of the phase encoding time, phase encoding gradient every time an MR signal is acquired. For 256 times, 256 times, 256 times, 256 pixel image, we have repeat phase encoding gradient 256 times along the y-axis. Omega 0 is the Rameau frequency. The sampling time t is used to apply the frequency encoding gradient in order to get the MR signal. The signal generated from an arbitrary point xy is given by this form. The MRI signal is the sum of all the signals generated across the slice. As a result, the MRI signal is written as this equation. Integration of the slice. So we have to do the area integral in the slice plane. And here phase change is given by this form. So rho xy is the spin density at the point xy. The integral is performed on the slice area. The phase exponential I omega 0 t can be extracted and omitted from the integral. Above equation can be expressed as follows if new variables are defined as kx and ky. Then we can write this equation like this in terms of kx and ky. So now the variables of signal is written in terms of kx and ky. Here signal was written in terms of gy and t. Gy is the slope of phase encoding gradient, and t is the time of the frequency encoding gradient. So this t means the data acquisition time. And we have to repeat 256 times of phase encoding process for the 256 times image resolution. So this gy, this variable gy and t can be changed to kx and ky. So kx is related to the data acquisition time t, and ky is related to the phase encoding gradient. The real space coordinates x and y are Fourier conjugate to kx and ky in k space. Nuclear spin density function rho xy and the MRI signal function skx ky are also Fourier pairs. The density function can then be obtained by inversely transforming the MRI signal functions as follows. So rho xy is the density function, and skx ky is the MRI signal function. This density function. The MRI signal function skx ky is represented as a signal frequency, a signal in a frequency space. So this is the function in the frequency space, so K space, but density function rho xy of nuclear spin is represented as an image in real space or image space. The variable K represents the spatial frequency and its dimension is 1 meter. The variables x and y, on the other hand, are real space coordinates with a meter dimension. The MR signal obtained using the pulse sequence technique is the signal in K space. As a result, the MR picture, MR image, can be generated using inverse Fourier transform of the MR signal in K space. So this is represented by the MR signal, and this gives the MR image. So this corresponds to K space, and this corresponds to image space or real space. The figure depicts the K space, MR data space. The pixels range from 64 by 64 to 512 by 512 in the image. So this pixel. The gradient GY, SGY, phase encoding gradient, must be changed 512 times along the y-axis to achieve the 512 phase encoding gradient process needed for the 512 by 512 pixel image. So for the 500 times 512 pixel image, we have to repeat phase encoding process 512 times. Each time, the slope of the phase encoding gradient should be changed. In each process, the MR signals are collected by applying Gx along the x-axis. So we can get MR signaled each phase encoding process by applying Fourier encoding gradient Gx along the x-axis. For each GY process, TR is required. Time of repetition is required. Hence, 512 TR times are used to generate one 512 by 112 pixel image. This results in 512 total time along the y-axis in the K-space. So in this direction, for each MR signal, we need time of TR. So if we do the Fourier encoding gradient process 512 times, then total time needed to fill this K space is 512 TR. And time for y-axis is thus 512 TR. This corresponds about a few minutes. On the other hand, TS represents the data collection time. This called data collection time along the x-axis, which is just a few milliseconds. So the x-axis and y-axis and k-space therefore have very different time scales. In this direction, y direction, the time scale is about a few minutes, but in this x direction, total time is just a few milliseconds. This is data acquisition time. And the MR signal has the highest strength in the middle. It is the middle. And its intensity decreases as it approaches toward edges. So intensity is decreasing if we move to the edges. Okay. Now let's see how to do sampling the data. The multi-resonance signal, MR signal, is an analog signal. However, in order for the computer to process the data, it requires a digital input. As a result, we must sample some data from the original analog signal. When it comes to sampling, more data can help improve image clarity. However, sampling a significant amount of data requires great data processing time. As a result, the best number of sampled data should be chosen by balancing the image resolution and processing time. The Nyquist theorem states that the number of sampling must be at least 2 per one period for maximum frequency signal in order to prevent aliasing and imaging. This means that the sampling interval this means that the sampling interval's inverse, this is sampling rate, must be twice as great as the maximum frequency F maximum, which will be demonstrated below. Here we have a sine wave. If we take two data per one period of the signal, this one, we can have this one, okay? We just pick two data per one cycle of the wave. We can have this picture. Nyquist theorem states that the number of sampling must be at least 2 per one period for maximum frequency signal in order to prevent aliasing and imaging. If we sample twice in a period here, as in the figure, we can infer that the signal being sampled reflects the sine function. So the sampled signal resemble the original signal. Now let's see the Fourier transform of Coulomb function. The data from the signal is sampled using the Coulomb function. The Coulomb function is made up of a series of delta functions that are evenly spaced. So this is the Coulomb function, a series of delta function, and between two delta function time is t. This Coulomb function's Fourier transform is also a Coulomb function. So if we Fourier transform of this Coulomb function, we can have this. This is also Coulomb function, but distance between successive delta function is now 1 over t. Here t, but if we Fourier transform this Coulomb function, we have the series of delta function, but the distance between delta function is now 1 over t. So Coulomb function is expressed by this equation, and if we do the Fourier transform of this delta function, Coulomb function, we have Coulomb function, but now the distance between delta function is 1 over t, and here t. In this slide, we show the Fourier transform of Coulomb function mathematically by Fourier series expansion. That's not Fourier transform. This is Fourier series expansion. The Coulomb function can be written as this form, this exponential form. The coefficient Cn, this coefficient Cn, can be determined by multiplying both sides with this exponential function and integrating over one period. Then we have Cnt, this side, and this side is written by this. Okay. Since the period of Coulomb function is t, and we are integrating between t0 and t0 plus t, so integrating over one period, so it follows that only one value of n apply to the integral range. Therefore, n should be 0. Thus, the coefficient of Cn can be obtained as n equals 0, 0. So delta t, right? So we have coefficient of Cn is given by 1 over t. Thus, Coulomb function can be written as this form, in the exponential form, like this. Now, the Fourier transform of this Coulomb function is given as, so if we do the Fourier transform of Coulomb function is here, and exponential integral of dt. And then if we put this one here, we can have finally this form. So in spatial domain, comp function has spacing t. So spacing t, while it has spacing 1 over t in the frequency domain. That's a Fourier transformed one. So Fourier transformed, comp function of Fourier transform that gives the function in the frequency domain. So in frequency domain, spacing is 1 over t, and the real domain spacing is t. But if we do the Fourier transform comp function, we will still have comp function, but spacings is different. This is MRI signal, sync function. If we do Fourier transform of this signal, we can have window function. And the bandwidth is 2f max, so minus f max to plus f max. MR signal is fundamentally sync function. The sync function becomes the window function when it undergoes Fourier transformation. Okay, so you can see this here. The comp functions is used to multiply the MR signal for sampling. For sampling, we multiply this signal by comp function. So multiply this signal and the comp function. Spacing is delta t. Then we have SY. And we know that if we do the Fourier transform of this comp function, we have still comp function, but spacing is now 1 over delta t. Okay. So combining these two results, we have this window function. If we do the Fourier transform of the functions, which is multiplied MR signal by the comp function. If we do this Fourier transform, then we can have the series of window function. Okay. The product of the continuous signal, this signal, with the sampling function, the comp function, in this case comp function, represent discrete sampling. The Fourier transform of the comp function with interval delta t between delta functions is comp function with the interval 1 over delta t between delta functions. So we still have a comp function, but the spacing is now different. Delta t and 1 over delta t. The window function array with the interval of delta t, 1 over delta t results from the Fourier transform of the collected data. So this gives the series of the window function. According to Nyquist theorem, the sampling rate 1 over delta t must be greater than twice the bandwidth in order to prevent window function from overlapping. So we can check the Nyquist theorem here. To prevent overlapping of this window function, 1 over delta t must be greater than twice of fmax. So this gives the Nyquist theorem. So we can check in this figures the Nyquist theorem.